All right, so let's continue with something more concrete. I gave you in the first lecture sort of introduction into where we're heading, um, trying to ask questions, what are we going to be discussing and why. So there was one last thing I wanted to cover, namely discuss um, kind of questions that were building up by that time and in what way they're resolved. So I'll actually first ask you some questions. So how many of you are familiar with 4D n equals 4 superring mills? So how would you characterize 4D n equals 4 superring mills? Maximal supersymmetry? Anything else interesting about it? Huh? Uh, that too, yes. Conformal, scale invariant, what else? Any other symmetries we should mention? Yeah, electric magnetic duality. All right, so that was warm-up question. So that's not a real question. More real question is, we're discussing all this sort of theories T of Mn obtained by compactification on some manifolds and so on and so forth. So that's all cool, and we're gonna go to a world of 2 or 3 manifolds, 4 manifolds, and they're quite rich. So why don't we start with a simple 2 manifold? So take a just 6D theory, 0-2 theory on a 2 torus. So 2 torus doesn't need any topological twist. It's very flat. Let's take the flat metric, so it preserves supersymmetry. So we should get maximally supersymmetric theory in 4 dimensions, right? Also, 2 torus has very natural SL2Z symmetry. That's basically its mapping class group. So we'll get a 4-dimensional theory, non-gravitational, with SL2Z symmetry. So how many of you think that the answer is going to be equal to 4D equals 4 superring mills? Any votes, yes or no? So how many of you think it's not going to be 4D n equals 4 superring mills? That's impossible, right? So why are you scared to vote? You're right that this is a trick question. But what's interesting is that 5 years ago, most people who raised their hand that they know what 4D n equals 4 mills would also raise the hand second time because, well, we thought we didn't know any other theories with maximal supersymmetry, SL2Z action, and so on. So the answer is actually it's not. So that's the modern perspective. In fact, in 10 minutes, I'll show you maybe 2 quick ways, not just one, but several ways to see that that's not correct. But can you guess? I mean, some of you, can you guess what could be wrong? What's going on here? How is it possible that they say that 4D n equals 4 superring mills so special with its theory without gravity and so on and so forth? It's so unique, so constrained. There is just a choice of gauge group. So there is a choice of G here. There is a choice of G on this side. Mm-hmm. Correct. So can you see, I mean, what else could it be, right? So can somebody propose an answer or any guesses? That's a hard question. Yeah, so that's part of it here. I mean compactification. Yeah, compactification. But you already probably anticipate the answer with this. Huh? Yeah, I start with NM fibranes. We'll look at world volume theory, which has no gravity, 6D02 of type G, I mean UN or SUN. So yeah, what's going on? All right, so I'm not gonna torture you, so we'll see the answer in a few minutes. But now I'll go to puzzle. So Um, with this choice of G, we'll work with either U1 or SU2 most of the time. So I already said that I love SU2 because it's simplest non-abelian group. So everything, when I don't specify group, it's always going to be SU2. But in this lecture, I'll try to illustrate that when questions become hard, like the one I just asked, 'cause it sounds like a tricky question, you can actually practice on experts. I mean, no kidding. Next week, those of you staying for next week, there'll be a lot of advanced talks and so on. Practice it on experts. See how many people will give you what kind of answers. And I'll try to, of course, give you the detailed version so you can have fun, entertain yourself. So, and the point of this lecture is when things get really hard with questions like this, try it on U1 first. It's also rank 1. I mean, it's simple enough. It shares a lot with SU2, same cartan, but SU2 has all kinds of non-abelianness. This is basically SU2 without non-abelianness. So that's the way to think about it. But anyway, here are the puzzles. That these are not homework questions. These are not research problems for you. These were puzzles that were around 2013 that many people, including myself, didn't quite know how to resolve. So these were real serious puzzles and issues. And one puzzle that was at the time is that with Tudor, Dimov, and David Gayot, we proposed class of theories in 3 dimensions, 3D n equals 2 theories, which were based on triangulations of 3 manifolds. And they're all Lagrangian. So there must be incompatibility with what I told you in the first lecture. And incompatibility is simply that just like this is not equal, I'll show you in a second, this is not equal to T of M3. So there are lots of things that didn't match. So basically, there are lots of things that triangulation approach is missing. So triangulations are missing all kinds of things. In particular, they're missing, I mean, just like in Lotta's talk, complex flat connections play a very important role in this 3D correspondence. I may have time to say about it next time, tomorrow. But among flat connections, simplest ones are the ones which are fully reducible. So basically, they live in a cartan of a complex group. And for my choice of SU2, complexification is SL2C. So it still has one-dimensional cartan, and that would correspond to abelian flat connections. On M3. So this created all kinds of puzzles back in the day. So those of you who are young, hopefully you never need to worry about it. Those of you who are old may kind of encountered or seeing this. People made all kinds of ridiculous claims that theory T of S3 breaks SUSY, is SUSY breaking theory. So some speculated that it broke it dynamically and whatnot. That I mean, we'll talk about this theory later today or tomorrow. We'll see it has plenty of BPS states, and something that has BPS states has to be non-trivial. It cannot just break supersymmetry, go to trivial vacuum. That's simply impossible. So that's incorrect. Not having abelian flat connections also has important consequences. Basically, it means that you can never hope to reconstruct. So can never reconstruct even the simplest quantum group invariant. So here my goal is to give you introduction into quantum group something, and I'll describe interesting new quantum group invariants. But the old ones of Witten, Reshetkin, and Turaev are based at quantum groups at roots of unity, and they involve abelian flat connections in crucial ways. So if you are missing that, then you have no such hope. So that seemed kind of wrong or odd. And then if you, so I showed you that in constructing 4 manifolds, we like to cut and glue along three manifolds. So you have three manifold as a cross section. And if for some reason in this picture that we get after compactification, so there is three-dimensional theory T of M3 in the middle, some two-dimensional boundary conditions, and so on and so forth. So there are all kinds of such cuttings and gluings that mathematicians package by the name functoriality. And basically, if you're not allowing all flat connections on cross-section, it means that you're losing all these properties, so you cannot cut and glue, and so on and so forth. And this was quite important because every three manifold has a billion flat connections. So a simple example of a billion flat connection is just connection A equals 0, okay? So it's not only a billion, it's completely trivial. So, and every three manifold, every four manifold in gauge theoretic context, always A equals 0 is a solution to your equations. That's pretty much true in every version of gauge theory, including the ones that we're going to be talking about. So this was a problem. Again, if you're young enough not to live through those days, to you it's not a problem, but back in the day it was a puzzle, and many of us spending a lot of time on triangulations, basically banging our heads because it seemed that something is not working. So some people encounter similar issues in the context of even compactification on Riemann surfaces when in the study of Fock and Goncharov, for various technical reasons, it was very hard to work with closed Riemann surfaces. Their assumptions always require that there is at least, if Riemann surface is of genus G, it requires that there is at least one marked point. So you're not allowed to consider a surface without punctures. So in old days, again, there was this important constraint. And the same story was with these three manifolds, that this theory simply didn't work if you try to close the manifold, namely remove all the cusps. So if there are cusps, which are analogs of punctures, then there was something to talk about. And it has, again, it's basically another way of saying that you're required to have no abelian flat connections. So this was problematic. It was not ideal, and it wasn't clear where the solution should be. But it was clear what was missing and what didn't work. Okay, so that was one kind of puzzle. Believe it or not, it has to do with this question above, and I'll come back to it. Okay, so that's one puzzle from old days. Many of us didn't know how to resolve it. Another puzzle had to do with again, same type of 202 theory. Let's say on four manifold cross T2. Okay, and we'll put it as background. That's always assumed in my lectures, that on a four, and here it will be holomorphic. So six-dimensional theory does not have enough symmetry or supersymmetry to be like fully topologically twisted, but this is pretty much the maximal thing you can have. So you can have almost all of its directions to be topologically invariant, and you can have two dimensions combined in some holomorphic combination so that there is no z-bar dependence, but things depend on z. And then basically people thought that there should be, the following should be true, that first of all, if you compactify on, let's say, M4, for instance, then you get this two-dimensional theory or two-dimensional 0-2 theory T of M4. And you can try to compute its elliptic, I mean, this holomorphic twist. What it does, it basically says that, well, anti-holomorphic dependence is Q exact, but if you introduce complex structure tau on a two torus, then things will depend holomorphically on tau, and there is some kind of partition function of this theory on a two torus, which depends holomorphically on tau, and that, of course, is elliptic genus. So you can consider elliptic genus of this theory T of M4, that's exactly the partition function on a two torus. Okay. So now you can go in another way. So you can take the same 6-dimensional setup and first compactify on a 2 torus, and then you get something. So back in the day, everybody thought that what you would get is 4D n equals 4 superring mills. In fact, it's easy to see that if you're trying to make this topological, then you would get Waffe-Witten twist of 4D n equals 4 superring mills on the same 4 manifold, of course. Now, 2 dimensions are hidden. 4 other dimensions are available to 4D n equals 4 superring mills. So we would get Waffe-Witten partition function, which is actually is a Q-series, and it has modular properties and all that. I mean, modular properties coming from the fact that this has electric magnetic duality. So obvious question was that they should be equal, or should be equal. At least that was expectation, and many papers said that, and there are lots of mistakes that have been made in the literature because of, again, this misunderstanding and this misunderstanding. But that's okay, because that's how progress moves. We sometimes, have limited understanding of certain phenomena, and until better evidence or understanding appears, it's okay to make mistakes. But it's important to correct them as we go forward. So that's part of my lecture today. I'll try to highlight in all of these several problems. In fact, you can probably see my original question has to do with this, what the issue is. So at first, this sounds like a nice proposal. There is nothing wrong with this, right? But then there are several obvious things you can try to calculate. And you can try to calculate, first of all, modular weight. So in both cases, you produce some Q-series in this calculation. And that's a kind of Q-series that encodes BPS spectrum, and a kind of Q-series that we're going to talk about in detail. But at this point, we just want to know, is there one, namely both sides are equal, or there are two different ones? And we have to actually, then it's more fun, because there are two Q-series invariants of 4 manifolds. And if they are not the same, that sounds pretty crazy. It sounds like we can have yet another cousin of Waffe-Witten partition function, right? So either way is actually very cool. But anyway, what was the puzzle back in the day? The puzzle was that if you compute its modular weight, you can do it in 2 different ways. So here, if you reduce on a 4 manifold, you can take anomaly of the 6-dimensional theory, which is extremely well known, take, say, anomaly polynomial, and just integrate that over 4 manifold. And you can work out the central charges for, let's ask you to, central charges of your theory T of M4. It's a 2-dimensional theory. It's not left and right symmetric, so it will have 2 central charges, C left and C right. So these are the answers for N5 branes. I'll give you the answer, N5 branes. You have the following. So C left is chi. So here, chi is Euler characteristic of the 4 manifold, Euler number, plus 2 chi plus 3 sigma times n cubed. And C right is something similar. It's halves, chi plus sigma. Sigma is the signature. N plus the same term. 2 chi plus 3 sigma n cubed. So this is a quick, easy calculation. You just take 6-dimensional anomaly, reduce it on a 4 manifold, and find what anomaly should be in 2 dimensions. This is a very robust argument that goes back to 't Hooft, who said that anomalies across all kinds of RG flows involving dimensional reductions or compactifications, to be more precise, and so on, should match. So that, of course, is true. Anomalies is something we definitely trust. So where is the problem? The problem is that if I were to guess what my modular weight of this object should be, I would probably compute gravitational anomaly, which is the difference of C left and C right. And you can see that this term would cancel. Here I have something like 1/2 chi times n plus, so yeah, what I would get is maybe half chi plus 3 half sigma times n. So that would be my modular weight, and if I work with SU2, I mean, it would be this times 2. But if you open a paper of Waffe and Witten, you can find what modular weight of the partition function is. I mean, they computed many examples and worked out general story, and then there was mathematical theory developed by many people, and the answer is this. It's chi over 2, okay, in fact, with a minus sign, okay? So that's very annoying. So that's what people noticed back 10 years ago, and nobody knew what to, at least I didn't know, and nobody I asked knew what to do with this. It seemed like a complete mismatch. So first question was about the sign. So could it be that something is wrong with the sign? Yeah. Yeah, that's SU2 answer. Yeah. But I mean, it doesn't help. So basically, you try to, yeah, so this is strictly speaking UN. If I remove U1, it's not going to move a needle. The problem is the following, that I claim actually sign is also off, so the sign is different, but one could say, okay, maybe there was a sign mistake, there should be plus, then we only have to explain this guy. But the problem is that signature never appears anywhere in Waffe-Witten story, and there is no way to get rid of it in this part of the story. So that's, the signature term is just complete mismatch. So, yeah. So that was kind of observed, and people threw hands in the air, shrugged, and yeah, nobody knew what to do about it, right? So, I mean, these are real puzzles that were around back in the day. So what's the answer? And how do we understand? So luckily today there are many ways to understand this, and that actually has to do, so the issue is the solution to all of these questions is pretty much the same. So, and it has intimately to do with the fact that the theories that we after, for example, this T of M3 are very non-Lagrangian, at least currently known Lagrangian description is available. And these are much more complicated than some naive guess we had back in the day. So that's the punchline. And here the answer is that these are, so that's a simple resolution. They don't have to be the same. And the answer is here that they're also not the same. So T of T2 is not for d n equals 4 superrank Mills. In fact, from here, you can deduce this one, and everything is consistent. So the only thing I have to explain is why. So what's going on? And around 2013, something else happened. So a study of generalized symmetries was starting to help us understanding of quantum field theory. And even in cases where we don't know much about or other details, we can also look more carefully at symmetries and their anomalies. And here I can give you 2 reasons to see both of these facts. And one reason or one argument is it won't take more than one blackboard. So it's very quick. But then I'll have to unpack it a little bit so to give you more intuitive explanation. So that if somebody asks you this question in the future, you can confidently raise your hand and say that answer is such and such. Okay, so maybe a couple of things about 6D02 theory. I'm not going to need any more of these details. So we don't have its Lagrangian description, but we do know roughly what the spectrum of fields is, and at least in a abelian case, when G is equal to U1, that's a single fibrane, you can actually say that this consists of 2-form field B. This is supposed to be self-dual. It obeys some self-duality equations. So H, which is dB, is self-dual. It has some number of scalars. Can somebody tell me how many? Any guess? It's a finite number, and it's between 1 and 10. Okay, so this is not supposed to be a trick question. In any case, I was just introducing notations. So I think I scared you with all my questions that you're not going to vote even on simple number. So there are 5 of them, and it has to do with the fact that you can think of the scalars as motion of 5 brane in transverse directions. So 5 brane world volume is 6-dimensional, and M theory it has 5 transverse directions. So they're parameterized by this world volume scalars phi 1 through phi 5. If you have more than one phi brane, then we have matrix valued scalars. In other words, you can think of it as a dual. And this has to do with the fact that you have S5 R symmetry, which rotates them. And then you also have fermions. I'm not going to use fermions. So fermions, let's say psi, they actually transform as a 4 representation of Lorentz group in 6 dimensions and SO5. So these are spinors, and again, I'm not going to use them very often, but it's good to know. So another thing that maybe I should say that relevant to my question, these are easy facts, and then kind of facts that you can textbooks going 30 years ago. More recent development around 2013 highlighted the two-form center symmetry. So because it's a center symmetry, I'll call it C. And this is a global symmetry of the theory. And for 2 cases that I'm interested in, if G is U1 or G is SU2, the values of C are such that in this case, and in this is Z mod 2Z, or I'll just write Z2. Okay. So this Z2 is a center of SU2. This U1 is the center of U1, and that's why it's called center symmetry. And it's a 2-form global symmetry of the theory. Okay. So now I promise that I need only one board. In fact, I'll use this one to show you that T of T2 is not for D n equals 4 superangles. Because if we perform dimensional reduction, so I'm not going to commit to either version. If you prefer, use abelian case. If you want SU2, use this case. In both cases, we have some 2-form symmetry. I'll call it C. Okay. Now I'm going to reduce the 6-dimensional theory on T2 and ask what kind of symmetries does this 2-form symmetry descend as I compactify my theory on T2. Okay. Well, I have a 2-form, and it can have various options. So 2-form can have both of its legs along T2. So then it's going to give me 0-form symmetry, which is, of course, going to be same C. So if my starting point was U1, I'll get the same U1. If my starting point was Z2, I'll get the same Z2. But it's going to be same symmetry, except that it will change degree. So if I integrate over 2 torus, if I have 2 of the legs of C along 2 torus, it will give rise to 0-form symmetry. If it has 1 leg along a 2 torus, it will give me 1-form symmetry and another 1-form symmetry, because basically there are 2 1-cycles of the T2. Here you can quickly see that what I'm reconstructing is a homology or Hodge diamond of a 2 torus. And if my 2-form symmetry has no legs on a 2 torus, it just descends to a 2-form symmetry of 4-dimensional T of T2. So what I'm describing is T of T2. And it will give rise to the 2-form symmetry. Okay. Now, if we are in non-abelian theory, there might be some discussion about choosing so-called polarization and so on, which will tell you that you have to get rid of one of the choices in either 1-form symmetries or half of the choices between 0-form and 2-form, but the other half will remain, okay? And this is an important point, because if you now look in 4D n equals 4 superangles, which is Lagrangian, what you'll find is that, yes, you have one-form electric and magnetic symmetries associated with the center of the gauge group, but there is nowhere in 4D n equals 4 either two-form or zero-form. So it doesn't matter if we make choice of polarization and so on, we just have no option for two-form and zero-form in 4D n equals 4 superangles. So therefore, again, symmetries simply don't match. There is no hope, no choice, okay? Very quick. I promised you this will be less than a blackboard. It is less than a blackboard. I mean, symmetries don't agree. So that's it. This is just the beginning. So look a little bit closer. And the same, of course, is going to be resolution to these other puzzles that we understand very well from present day perspective. So if you look a little bit closer, we'll notice that the following, that what is R symmetry of 4D n equals 4 superangles? Please try to answer this. I mean, many of you raised your hand that you're comfortable with 4D n equals 4 superangles. I know I scared you, but try to vote, okay? But just tell me, what is R symmetry? SU4? Okay, very good. I'll write it as SO6 with permission. 4D n equals 4 superangles has SO6 R symmetry. So this system, compactified on T2, does not have SO6R symmetry because I have only SO5 over there, and as long as I keep my two torus as a two torus with a periodic direction, there is no way I can do anything rotating this dimension into one of the non-compact dimensions transfers to the fibrane. It's just not a symmetry. So therefore, at the level of R symmetry, so that's actually more funny. So in this theory, we get for T of T2, R symmetry is SO5, maybe times a discrete group and whatnot, but not SO6. So we have several maximally supersymmetric theories in 4 dimensions, all non-gravitational, both have SL2Z symmetry. 4D n equals 4 has SL2Z of electric magnetic duality. This has symmetry of tori, I mean of mapping class group of T2. So they have a lot in common, but some things are not the same. Our symmetries are different, these two-form symmetries are different, and I'll give you one more explanation, so it will be number 3, actually, illustrating where this. So here the culprit was two-form or zero-form symmetries. And this is something that we can describe. And all of these are kind of related. So the fact that you have smaller R symmetry, SO5 instead of SO6, and here you have this different zero form and two forms, which are not in 4D n equals 4 superangles, are all connected together and also to the geometry of the moduli space. Okay. So let's analyze quickly the moduli space. So I told you that when in doubt, it's always good to consider U1 case. Hopefully, I managed to put you in doubt about what these theories are. And therefore, let's practice with abelian cases. So I'm going to consider which is going to be n-dimensional torus. And I'll, again, start with U1, but then it's going to be very similar, basically, at the level of moduli spaces where you have abelianization and so on, SU2 will differ from U1 by sometimes taking Z2 quotients. But most of the things we can see already here in the case of U1, because notice that this problem I could have phrased just for single fibrine theory, which has U1 gauge group. It's almost Lagrangian. So let's start easy. So n equals 1 case first. So first I compactify on a circle. And here we're not going to suspect too many problems. Yeah. No, it has little to do with that. It has to do, it has to do with what exactly, how you define class S theory. If you define it, so I'll sort of decode it in a second. And this was not clear in the beginning. Even so, this question actually persists in class S. Of course, what I say about T2, you can ask for any Riemann surface sigma. Anyway, let me come back to this. So yeah, that's true. So until recently, there was not even a clear understanding in the case of class S, because people would say theory of class S for T2 is just for the n equals 4 supermills. That was part of the mantra that you know many of us, including myself, of course, made mistakes about. But anyway, so let's just walk slowly and see where the issue is. It will be very visible, just like here. I mean, there is no way to get out of the fact that you have to choose between this, and it's just not part of 4D n equals 4 superangles. I mean, 4D n equals 4 superangles has no 2 form or 0 form, period. So that's it. But anyway, so what's the issue is? We're gonna be, to resolve the problem, we can go back to Kalutz and Klein. If everything is abelian, free, so the point is that 6-dimensional theory with single fibrane, it's a free theory. Yes, it has self-dual 2 form, but because everything is free, we can just do the reduction. So here the question is, T of S1, is it really 5D maximally supersymmetric superang-Mills? So that's actually a good question. I don't know the answer. So if I were asking this question instead of my original one, this would be more tricky. So I don't know the answer. There is a good chance that the answer is yes. So I may try to erase my question mark, but at least that's the general belief. Okay. But even here, there are some interesting questions. So we can do the most boring in this case, dimensional reduction, sorry, compactification, a la Kalutz and Klein. And again, we have spectrum of fields B, some fermions, and we can just reduce them on a circle, right? So it's not really rocket science. We're talking about free fields. So Kalutz and Klein taught us how to reduce free fields on circle. So we gotta be able to do that. I mean, that should be really easy. So B field reduces to gauge connection A. So if B has one leg on a circle, then it produces one form. So that's perfect for our gauge field. So this will be one form or gauge field. I don't know how to write. And in fact, we don't have to worry about other choices if B does not have one leg on a circle, because self-duality kind of removes those other choices for us. So in 5D, we don't even have to worry about any other things. So it just gives A, that's good. So from scalars, not much is going to happen because scalar is already a 0 form. So there is not much to reduce. So it will remain as a set of scalars. Maybe the only thing we have to care about is that now there is this Kalutz and index M associated with winding around the circle, right? So it can have momentum. So this is what we call Kalutz-Klein modes, especially when M is not equal to 0. And same for spinors. So if we have spinors, we'll get psi m for these integers. And in fact, that's also true for my gauge field. So we'll have a whole collection of such guys. I mean, there are also massive modes of B associated with Kalutz-Klein modes. So now, if I compare the spectrum of fields that I found to 5D superang-Mills. So this is going to be my mass of the state, and this is the spectrum. What I see, a la Kalutz and Klein, is that I have integral spacing between states. Again, that's Kalutz and Klein would definitely endorse it. They understood it more than 100 years ago. There is nothing new I'm telling you about. But 5D superang-Mills contains massless fields. It has gauge field with index equals 0. It has scalars, yes, that's right. Same scalars, but only m equals 0 part. Same for spinors. Okay, so if I draw on this diagram where 5D superang-Mills spectrum lives, it's actually here. It's only 0 modes of these fields, right? So that's going to be 5D superang-Mills. And then the question is, how can on Earth we explain in 5D superang-Mills even an abelian Maxwell theory? Notice that there is nothing non-abelian here. I'm describing just reduction for G equals U1. So how in maximally supersymmetric Maxwell theory can I have these other states or fields? What explains for the rest of the Kaluza-Klein tower? Okay, this is actually very serious. It's not a homework. It's a research problem, and that's kind of cutting edge of our understanding of the field. But this is subtle. However, if you go and increase dimension of, actually, I'm going to use the same board. Yeah, if you increase the dimension n, things will become more and more apparent. In other words, the more circles I'm going to take, the more fun we're going to have seeing that it quickly deviates from naive Lagrangian expectation. So I'm going to do this next. But I'm actually going to reuse this board. It's easier for me. Are there any questions in the meantime? Because I'll mess up some things on the board. Yeah. Huh? So two form so already in 5D, two form disappears. So if we consider six-dimensional theory on S1, so two form has two options. It either may not have any legs on S1, or it may have one leg on S1, because it's a two form. Because it's self-dual, I may commit to one of these two choices, and that's good enough. And in 5 dimensions, two forms and one forms are dual. So therefore, if I choose one, I don't have to worry about the other. So that's where it's gone. So I made a choice where I decide to use it as a one form, but I could have stuck with a two form. Basically, what I'm saying is that self-duality gets removed after we compactify on a circle. Okay, any other questions? Okay, so let's go to closer to where we care, what we care about. So let's do T of T2, okay? So now this is gonna be our usual question mark. I'll change 5 to 4. We still have this Kaluza-Klein tower, and so on and so forth. So let's maybe first do carefully reduction of the spectrum, right? So I start, in fact, let's see, maybe, yeah, I can actually continue, right? So now I cleared the space, so I can do this. So when we go further, we can say what's going to happen after another circle reduction. So basically do it step by step. On circle, then another circle. So as we reduce gauge fields, what's going to happen is that we gauge fields in 4 dimensions. But now, because we already had a gauge field 0 form A, which didn't have any m equals 0 or no Kaluza-Klein mode, we can actually have periodic scalar describing its holonomy. So important point is that this phi takes value in a group, in a gauge group. It's holonomy. It's a holonomy of 5-dimensional gauge field around a circle, right? Holonomy of a 5-dimensional on a circle. And holonomy by definition is element of the group. So then scalars become scalars. So phi m becomes phi m, maybe comma n. So now I have two Kaluza-Klein indices because I have two cycles of the tori. And psi also becomes psi m comma n, right? So you already start seeing what's interesting, what's different. What's different between 4D superrank Mills, even in a abelian case, it would be Maxwell theory. And this theory, T of T2, is this guy here. This is the whole point. And that's responsible for all our puzzles that we had before. So this is, if we have, in the U1 case, circle-valued scalar, it does have both 0 form, which is just rotating the value of the scalar, and 2 form, which is dual magnetic symmetry. So surely you have that. So that explains, indeed, we got correctly these guys, and they have to do with the fact that the circle, the scalar is periodic or group valued. And it does have to do with the fact that we got only SO5 and not SO6 R symmetry, because every other scalar is adjoint valued, right? Or in U1 case, it would be R valued, not a circle valued. So that's what's happening. So in fact, you can see this very clearly if you try to write the Coulomb branch of this theory or moduli space. So moduli spaces or Coulomb branches show this very clearly. So Coulomb branch of U1 four-dimensional superring mills is just this. It's what people call U-plane. I mean, it's a complex plane. It's basically a copy of C. Okay. So this is 4D superring mills. But in this theory, T of T2, analogous picture would be combining one of these real valued scalars phi with the periodic fellow there, so that we have a cylinder, also known as C star. So, well, clearly they're different. So now, if I ask you, is this theory the same? Clearly not. In fact, this picture clearly accounts for everything I said so far, our symmetries, this generalized symmetries, and so on. And things are going to get worse and worse if we compactify on more and more circles to get T of T3 and so on and so forth. Yes? Well, I would prefer to have it smaller size. Usually people take limit where volume goes to 0. What I'm pointing out in that old language is that, yeah, so that was indeed old language, why we believed and so on, that this is 4D superring mills. The point is that the limit is not smooth. So there are many functions in mathematics where limit of the function differs from the value at the point where you're trying to take the limit. Well, no, still the same. The point is, as long, yeah, so here the issue is not so much whether it's large or small. The point is, do I lose this holonomy ever? Do I ever break the torus or circle, tear it apart so it becomes open? So that operation is clearly not allowed, and the point is that that operation is highly non-smooth. So it's a mistake to think that limit equals limiting value, or a value of function at that point. So yeah, these are not the same. So this was the story for U1. If you take as U2, not much is happening because in right in 4D n equals, yeah, so for D equals SU2, this is more maybe like extra credit, or I mean, I hope I made the point, so this is just more for fun. So what happens is that when you have SU2, SU2 behaves very much like U1, but you have to divide various things by Z2 sometimes. And in particular, if I go through this reduction process that I did slowly, what happens is that I have to chop this picture of periodic scalar times R-valued scalar by Z2. So I'll get half of it, and I'll get a picture kind of like this. It will have two singularities, and will be asymptotic to C star as we go to large radius, but it will be cylindrical. I mean, asymptotic still not going to change. So everything I'm saying can be viewed, visible semi-classically when vevs of some fields are very large. So that's usually semi-classical regime. So here for SU2 superring mills, there is one singular fiber in a plane which still looks like a plane. Asymptotics didn't change. We have one singular fiber, so that's where the elliptic curve or spectral curve shrinks or degenerates. One of the cycles becomes singular. And this is the singularity known as I0 star. And if you ask what is the monodromy of this singularity of basic periods at the singularity as we go around, it's going to be minus the identity. Okay. Whereas here, if I go around this region at infinity, What's the monodromy? You can actually quickly conclude that it's plus identity. Okay, and of course, what happens is that in this picture there are two singular points, each of which looks very much like 4D superrank Mills, but there are two of them. And of course, it's consistent that if I go around this plus this, monodromy is -1 times -1 equals +1. So everything fits. But it's important that now we see in SU2 case that my theory T of T2 consists of two copies. So it's actually more, way more than single copy of 4D n equals 4 superrank Mills, but two of them glued together in interacting way via moduli space. So if I'm computing some indices and so on and so forth, I can expect, and actually that's a good intuition, that some BPS partition functions, indices, whatever we get from localization, if there is ever localization, here is roughly twice as big as this. Because there are two such contributions at singular points, but again, we cannot easily say that it's really twice because they interact via some maybe not as non-abelian, but still non-trivial matter on the rest of the Coulomb branch. Okay? Yeah. I don't know. That's a good question. Why didn't anybody raise their hand? I asked the question, right? I asked the question in the beginning. Are they equal? And people, huh? Well, exactly. Right. Papers on this too. You of course know this. Yeah. Exactly. Exactly. Yeah. So Nekrasov. Yeah. So I think it's interesting that even yeah, so you're right that there were definitely important lessons and hints that some people could have envisioned, but I don't know to what extent even Nikita would actually say this as clearly, for instance, say elliptic genus mismatch versus this Vafa-Witten partition function. Now we have so many pieces that, yes, it fits together. So at this point, it doesn't matter. I'm just pointing out to younger people that they shouldn't fall into this trap. But since you pointed this out, it's a very good way to summarize the lesson. So the lesson, the difference between these moduli spaces, the way Nikita would actually describe it, he would say that everything four-dimensional is, if you do, again, computations like localization and so on, that's what he cared about, this would be homological. So he would work with equivariant homology for various moduli spaces and so on. This one, the way the picture differs in our T of T2 versus n equals 4 superrank Mills is that this is K-theoretic. So that's one way to say it, that you work with K-theoretic moduli spaces where things are group valued or periodic or you study indices. Another point is that Kaluza-Klein modes are actually important. So this is something that I didn't discuss when I was drawing this Kaluza-Klein tower, that you can ask, how does it explain mismatch of C left and C right that we got in the other part? So this is another interesting thing. There are several things that's happening. So in this tower, even at the level of zero modes that we saw, it's very important to have periodic versus non-periodic scalars. So that's important. But also, even non-zero modes, so I think this was not known to Nekrasov, contribute in a way that change anomalies of the theory. So this is more subtle, because usually we expect that massive modes, or Kaluza-Klein modes, don't change anomalies or low energy effective field theory. But here what happens is that yes, each individual one maybe doesn't, but there are infinitely many of them. So you basically get into this game of 0 times infinity, and sometimes it may change the answer. So this is more subtle. I believe this was not known to Nikita, but the way I would phrase it in his language is that what's important is that whenever we compactify, we get this very nonlinear moduli spaces or K-theoretic type of moduli spaces. That's the nonlinearity of asymptotics here versus very linear asymptotics in the other case. So there are stark contrasts. Sometimes when I used to give talks on this, I put K-theory and KK together and people object, so which is probably the right thing to do. Okay, any other questions? So hopefully this explains why naive things, again, back like 10 or 20 years ago were not okay. So since we're talking about this Kalouza-Klein reduction, let's do a simple exercise. So I told you that it's a good idea. So maybe I'm going to continue a little bit further down this tower. But if I'll work with U1, that nothing prevents me from being quite general. So we can assume, just for fun, that yeah. So let's consider T of M4 for G equals U1, just like over there. So we have, yeah, this is a simple exercise. So I'll work it for you so we can see what the spectrum looks like. So we have H, which is dB, and H equals star H. So this is the only interesting ingredient in this reduction, the two form. And to keep things simple, let's start first with simply connected M4. So 4 manifold is can be characterized by many Betti numbers. So it has so Betti numbers will be B0 equals 1 because I want connected manifold. So it has B1, which tells me how many one cycles I have in a 4 manifold. And for simplicity, I'll assume that this is 0, but only temporarily. We can easily relax this. In fact, we'll do it in a second. And then you have two-dimensional homology and its dimensions, which are actually of two types. So there is B2 plus and B2 minus, because there could be self-dual and anti-self-dual two forms. And then if I go to B3, B4, they reflect or they're not independent by Poincare duality. So the only thing I have to do is to, the only non-trivial piece of this exercise, in fact, as you can anticipate from what's happened here, because if my manifold is simply connected, then it doesn't have any one cycles, and my spinors, and I'm not even going to worry about fermions actually, but my scalars are zero forms. So they just descend in a very straightforward way, and I'll comment on this in a second. But let's look at the most interesting part, which is this self-dual two form. So it will give me some scalars in two dimensions. And the fact that it's self-dual translates into the fact that the scalars will be chiral. So they'll be left moving or right moving. That's something I was emphasizing this morning. And it has direct relation to the fact that central charges left and right will be different for these theories. So in particular, I can write this H in the mode decomposition. And I can use the basis of self-dual and anti-self-dual two forms. So for instance, I can use omega I plus and write sum over I from 1 up to B2 plus, and then a similar term over J from 1 up to B2 minus of something times omega J minus. And then I have to wedge this with derivatives of my mode decomposition of this B, so I have to give name to this mode. So this will be basically del derivative, holomorphic derivative of some left-moving scalars xj and anti-holomorphic derivatives in my notation from this morning of right-moving scalars xi. Okay. So important point is that, so my spectrum of two-dimensional theory will have the following bosonic degrees of freedom. It will have x left and x right. And in both cases, this will be compact. And compact for the same reason as our curly phi was compact, because it's made from gauge field, two-form gauge field in 6 dimensions. So it basically consider its holonomies over 2 cycles, and these are compact scalars. So these are compact, and these are also chiral. So there are 2 interesting features, again, both of which we see even in boring abelian case of a free theory. So these are right-moving. That's why they show up with the derivative del bar. And these are left-moving in 2 dimensions. That's why they show up with derivative del. Okay. So that's all. That's 2-dimensional spectrum that we get from self-dual 2 form in the U1 case. So I'm going to skip fermions because they're going to complete everything to supersymmetric multiplets, or for simplicity, either way. So next thing, I'll consider what happens to scalars. So this 5 scalars in the 6-dimensional theory. And when we put the theory, so this is requires a little bit of attention, not too much. In original theory, these are R5 valued because there are 5 of them, and before we put this 6-dimensional theory on a 4-manifold or wrap a 5 brane on a 4-manifold, these are just non-compact scalars, and that's why we have this SO5R symmetry and so on and so forth. But when we compactify theory on a general 4-manifold, we have to do something to preserve supersymmetry. Namely, we have to do topological twist. And here there are a couple of choices. And the choice that's relevant for us, that preserves exactly the 0-2 supersymmetry, otherwise the amount could have been different, is where this 5-dimensional space decomposes as space of self-dual 2 forms on a 4-manifold. This is 3-dimensional, and then there is our 2 piece, which goes for the right, nothing happens to it. So in other words, we have to split our 5 scalars into 3 plus 2, and something interesting happens to the 3 of them. They get identified with the self-dual 2 forms, and 2 of them do nothing. Okay. As a result, I can continue. I can say that from these 2, I'll combine them in a complex combination. So this will be C-valued, non-chiral scalar in 2 dimensions. Again, Kaluza-Klein reduction of scalars is very boring. We don't need Kaluza and Klein for that because they're not forms, they cannot trap anything, they don't wind, so that's it. It just, the scalars become scalars, they inherit their property from parent theory. So the only interesting thing may happen to these 3 guys. So because of them, we'll have as many, so they'll multiply, and they'll multiply by how many globally self-dual 2 forms we have on a 4-manifold. So as a result of these fellows, we'll have contribution here, which I'll call sigma. Let's see, sigma I. I hope my notations are reasonably consistent. So this will be a non-compact, meaning R-valued, non-compact, real, and non-chiral. Okay. So this is the bosonic spectrum of the 2-dimensional theory. From this, we can try to compute its central charge. So I'll try to calculate here. Okay, so first let's do C left. and I'll save myself a little bit of space. Right. So what's the central charge of one real boson? 1. Thank you. I'm just checking. Okay, good. So here we have, so let's start with easy things. In the left moving sector, basically I have to go through this table and ask, and complete it by fermions, so fermions, and ask what do I see in the left side, or left moving. Again, we're talking about free theory. So here we have this C-valued, non-chiral. This is definitely most boring part of the spectrum. So we have 2 real scalars. I'll write 2 for them. Okay, contribution to C left. Again, theory is non-interacting, so there is no worry that our counting is going to be exact. Now, I also see left moving fellow here, and this guy. Yeah, so maybe it's easier to write their number. So left moving xj, so J are these guys. Right. So as a result, I have 2 plus B2 plus. These are non-compact circle value, just R-valued scalars in my spectrum, plus B2 minus compact periodic scalars. So these are the X guys. And these are sigmas and phis, okay? I mean, they inherit compactness or non-compactness from whether they come from scalars in 6 dimensions or the gauge 2 form. Okay, so that's it. I'll note that this happens to be Euler number of the 4 manifold, and if you relaxed the condition that it's simply connected, the answer would still be true, that C left is equal to chi, and yeah, and actually it agrees with the formula I showed you before if you set n equals 1 and remove the cubic term from the C left and C right that I showed you a moment ago. So actually that's another consistency check, that it matches a reduction of anomaly polynomial. So in the U1 case, that's exactly what the answer is. But we can also count it by hand, and it's good that we match anomaly computation to direct count. So for C right, it's a little bit longer. So we have again 2 plus B2 plus. These are non-compact, in fact, same non-compact scalars, phi and sigma, because they're not chiral. They have left and right components, so they contribute to both. Now, on the right sector, we have supersymmetry. So, and by the way, yeah, sorry, and actually, maybe let's do the following. Sorry. Yeah. So first, I address the all scalar fields. So these are again non-compact. This is same as my fields sigma and phi. And this is going to be circle valued. This is compact field set of fields X. Okay. So what's going to happen is some of them will combine together, because in the right moving sector we have supersymmetry. We have n equals 2 supersymmetry, so all scalars have to be part of supersymmetry multiplet. And that means 2 things. First of all, they have to be complex valued. And secondly, they have to be accompanied by fermions. So complex valued is easy to arrange because phi is already naturally complex valued the way I wrote it. And now we have the same number of non-compact sigmas and as compact x's. So actually we start seeing the same phenomenon we saw here, that something compact and non-compact will combine in C star valued combination. So namely, the sigmas and this x's will naturally be parameterized by sigma plus ix which is C star valued, or if you wish, exponential of that. So that's a natural parameterization here. And we have 2+ copies of these guys. So we have two-dimensional so-called 0-2 chiral multiplets, which are parameterizing, take values in C star. And that's, again, same feel or same aspect that we saw a moment ago in, in this story, in high dimensions. But now there are more of them, and that's why I said that the further we compactify, the more pronounced the effect is, the more periodicities we have. And of course, now it's no surprise that in 2 dimensions, periodic scalars give us symmetries, electric or magnetic, or winding and momentum, respectively. In this case, both are going to be zero-form symmetries. And this is something classical, super well known. So here, again, it's completely clear what the analog of the previous phenomenon is. So it just gets pronounced. Okay, but we have to, or I have to continue because I have to add fermions, and I found from here B2 plus 1 chiral multiplets already, so I know that there should be fermions, and maybe you trust me that that's exactly how many fermions we get if I follow this Kaluza-Klein reduction, and each fermion contributes 1/2 to the central charge, so I get, and if you compare this with anomaly polynomial computation that I showed you without proof a moment ago, it's going to match perfectly. So you can consider this as a proof of the anomaly computation that I showed you without the derivation. Okay, any questions? So this illustrates that, again, when in doubt, consider abelian theory. It's not a big deal. It's a lot of fun. And it's trivial compared to what Klein did. So computation didn't take as much space. I mean, their paper is more detailed because of gravity. So here you can see that why this is a baby version of string theory compactification. A lot of things come from gravity in string theory. Here, you don't have that. You don't have gravity. So things are much, much simpler. And again, scalars, fermions don't contribute too much. The only interesting thing is what happens with gauge fields, especially if they're starting life as two-form gauge. So I already gave you some number of homeworks. I forget how many, maybe 1 or 2. So let's say that it is 3. Just so it doesn't have with any previous numbers. It doesn't matter if my numbers are in order, I think, as long as they're not overlapping. So homework is work out T of M3 for G equals U1. Basically do the same exercise as what I did here for 3 manifolds, because I worked out for you T of T2. You can actually try to work out that for, in the abelian case, for any genus G surface. That would be relevant to class S discussion and so on. You'll also see how many higher form symmetries and so on you have, whether it matches. That's why it actually, I don't know if it agrees with what people call class S theory. That would be more fun. There is order of limits and so on. But in any case, just for you want to work out what this is. And this is homework number 1. And maybe homework or homework 3. Homework 4 is, this is slightly more interesting. Work out space of vacua analogous to what I was showing you before for T of T3. Okay, so this is maximally supersymmetric theory in 3 dimensions for GSU2. Sorry, I should have said simplest non-abelian case. So this is, I mean, you can start with U1, yeah, because this will be part of your homework here, but then try to generalize it to SU2. And what you're gonna see is something interesting. You can compare it to ABGM theory, which is also maximally supersymmetric theory in 3 dimensions, but you can see how they differ. And again, even for SU2, you'll see useful lessons analogous to what we saw a moment ago. Okay. So any questions? So one important point, which is consequence of, so I'll call it remark or lesson. One lesson from what we saw is the following. As you go down in dimension, especially if topology of your manifold is richer, like for 2 torus is much richer than for a circle, and for general 3 or 4 manifold with lots of cycles, it will be bigger and bigger. What we see is that we get group valued fields. And in writing of either 3-dimensional n equals 2 supersymmetry or 2-dimensional 0, 2 supersymmetry, everything has to be chiral, and fields have to be complex valued. So they're actually complexified. So what we see, what's an important point is that we don't know exactly what this T of M3 is in general, or M4, but we know that it's a theory. So that's why I don't know how to write Lagrangian for it, but it's clear that a theory with very nonlinear matter. So in particular, we should have all kinds of, so I'll just write lots of GC valued fields. So this is something that's not terribly unnatural because we have nonlinear sigma models. All I'm saying is that we have kind of nonlinear gauged sigma model where we have group valued fields, and I mean, it obviously has G action on it and so on and so forth. So, but we don't usually, when we do like localization computations, we don't do localization with such non-abelian matter. We usually assume that our representation of the gauge group is linear. It's basically vector space on which there is some G action. And that's the crucial difference. So I think this is something doable. This is a problem that you can work out. It's a good project for a paper. And with Sang-Uk Park here and others, we had a preliminary kind of discussion of this in one of the papers, but clearly a lot more work needs to be done. So this is based on work with Nikita Sepenko, Sang-Uk Park, Porsche and Xin. I forget who else is on the paper. Oh, maybe not. Was Porsche there? No, right? Okay, see, my memory, okay. So I'll just put ... because I didn't mess up you two guys, I hope. Okay, so yeah, in that paper, we talk about calling them skyrmion models. Because Tom Skyrmy, when he was proposing the model for hadrons, he was basically suggesting the same thing. Let's describe it using group valued fields, and that's again the crucial feature of such theories. So that's why they don't fit Lagrangian description. And yes, you can extract naive Lagrangians if you approximate singular points and moduli spaces by their conical versions. So then we'll get something which is Lagrangian and so on, like Sicilian theories. But this has nothing to do with an actual T of M3 or T of M4. So they're much more nonlinear with more periodic directions and moduli spaces. And again, now we can luckily see this from generalized symmetries, all kinds of things. So my next goal is I try to illustrate, again, abelian case, use it as a test bed. So again, if in doubt, always do abelian case. My next goal is gonna move on to highly non-abelian case and extract information about the BPS spectrum. Here, in abelian case, I could do everything. In fact, that's part of your homework. So you can actually write the whole theory. So you can actually see what the theory is. So in particular, you can analyze its generalized symmetries if you like, and so on and so forth. But in non-abelian case, I'll be able to only compute for you some partition functions, but I still don't know what the theory is, precisely because it's a Skirmy-like theory. So my next job is to prepare us for that calculation, and yeah, so that's my goal. And I'll start with a. I have exactly 8 minutes, so I'll try to use it wisely. So I'll start by enumerating contributions to two-dimensional elliptic genus from basic multiplets. So here we saw that we end up with a theory of some chiral multiplets in 0-2 version. If I were to do three-dimensional case, I would have analogous three-dimensional n equals 2 chiral multiplets. So let me go back to this Q-series computations. And Q-series will be the subject of great detail in the next lecture. So 2D n equals 0-2 elliptic genus, so some basics. So there are essentially two types of multiplets you have to know about or worry about with 0-2 supersymmetry, or 3. But as far as matter goes, that's what we found here. There are Fermi multiplets, which consist of two left-moving, so these are two, well, I would say complex, two real-valued or two complex-valued left fermions. By complex, I mean while. If I say real, it would be Majorana while. We are in 2 dimensions, so that makes sense. Yeah, so we have just, I don't know, psi, I'll call it psi left, for instance. And its contribution to elliptic genus is just a theta function. So it can be written in a number of different ways. For instance, you can write it as Pachheimer or Q-Pachheimer symbol that we introduced before. So I'll write it as xq infinity times qx q infinity, where I can identify different parts. So notice that this is infinite product, and if I were in quantum mechanical problem, my contribution to the partition function of a fermion or index would be 1 minus x, where x is fugacity associated with rotation of the complex phase of the fermion. Since it's a complex number, I'm allowed to rotate between these two real components, so it has a symmetry, and later you may want to gauge some symmetry and so on. So it's good to introduce this as a fugacity. And in quantum mechanical story, it would be just this as a numerator. And because here we have lots of descendants, two-dimensional theory is infinitely many harmonic oscillators in the bosonic case, or infinitely many descendants of a fermion. So what we get here is contribution from del minus nth derivative of my fermion psi left, or psi minus, I don't know what's the best way to call it. And these are analogous contributions del n of psi left bar. So because it's a bar, it has opposite phase response to my symmetry. So that's why you have the inverse here, and there is a subtle issue where you start counting with 0, 1, so that's why there are some powers of q's dispersed in there. Okay. So similarly, yeah, maybe one remark. So this is contribution to elliptic genus. Well, actually, yeah, hold on. Let me continue. I'll make remark later. Yeah, maybe let's do these things first. Okay, so another multiplet is a chiral multiplet. So that consists of phi, which is complex scalar. That's going to be the right moving part of 0, 2 supersymmetry. And it consists of psi right, which is complex, just like there, complex right moving fermion. So contribution of this fellow is roughly 1 over theta function. So a lot of these things that we see will go in a denominator. More precisely, what it's going to be is the following. It's 1 minus x inverse divided by Heimers. So it's going to be x, or maybe for balance, I'll write it out. 0 to 1 minus x q to the n, 1 minus x inverse q to the n. And these are different contributions similar to the above. For instance, derivative of phi, descendants of phi, descendants of phi bar, just like for fermion. And this is zero mode, fermion zero mode. Okay. So you can actually combine it and write, cancel the first term here in this product with this term and write it in a form similar to the above. Okay. And this is the two-dimensional 0-2 story. But if your theory, so remember this morning we were talking about, we saw two-dimensional 0-2 theories naturally arise on a boundary of 3D n equals 2 theories. So if this is 3D n equals 2, and this is 2D 0-2 boundary, then you can also put together some basic building blocks for 3D n equals 2 multiplets. The way they can restrict to various boundary conditions. You have many different choices. In fact, there are infinitely many boundary conditions in the world that you can impose. So I'll just give you a couple of small ones. So to Chuck, for instance, if you start with 3D n equals 2 chiral multiplet and impose, oops, that's the same color, and impose Dirichlet boundary conditions, you'll get this part. So this is contribution of 3D n equals 2 chiral multiplet with Dirichlet boundary conditions. On the other hand, this component, this part of the spectrum, would be contribution of 3D n equals 2 chiral with Newman boundary conditions. And in addition, if you have a vector, which could be either two-dimensional vector or you can think of it as 3D n equals 2 vector with Neumann boundary conditions, then the rule is very simple, at least in a abelian case. We're going to discuss non-abelian case tomorrow. The rule is very simple. This fugacity x, which corresponds to phase rotation, so this was our symmetry, unless we gauge it, it's a global symmetry, but when we build gauge theories, we put together matter and gauge fields in a consistent way so that we're gauging the symmetry. So what it does, it basically requires physical objects to be gauged in invariant combinations. And in practice, if you have some contributions here from various fields, such that they have individual phase rotations under this particular symmetry, gauge invariant combinations means that you pick out essentially things which are independent have zero charge. So this is the Gauss law constraint, basically. And this means that at the level of partition function, this 3D to D elliptic genus, now I'm generalizing how elliptic genus would extend to three-dimensional fields as well. So what happens is you basically pick out contribution from the singlets, and this is achieved by integrating over X with this measure, which basically picks out the constant term in the sense of X expansion. So expand, pretend that you multiply all your spectrum, all the fields that you have, expand it out, using Mathematica expand, and pick out the constant term with respect to X dependence. So this is basically, so this is known as constant term, or it picks out gauge invariant combinations. Okay. All right, so I think I'll stop here, and we have everything we need prepared for exciting stuff tomorrow. So thank you for your attention.